Numerical Computation, Chapter 6, Video 1. We study direct methods for systems of linear equations. Here's the problem that we will be studying. We have n unknowns and we have n linear equations. In the general form, we can write it as following. Since each equation is linear in our unknown, we will sort our unknown to be x1, x2, and all the way to xn, and each is multiplied by some coefficients. We label it with a double index, a11, a12, a1n, and that's for equation 1. And then you have equation 2, where you change the first index into 2, so a21, a22, and so on, and then all the way down to the nth equation. So if the coefficients, the aij's, are nice in certain sense, then this system has a unique solution. Now we write it into a matrix vector form. So we think the unknowns x, we line them up into a column vector and we call it x vector. And the right hand side b, we do the same thing, we form a vector b. Then the system can be written as a matrix A times x equals to b, where A is a m by n square matrix. Its coefficients are exactly the coefficients in front of the axis in the system here as we prepared in the corresponding position. So it will be a11, a12, the first row, and the second row a21, a22, and so on until the last row. We shall be familiar with this procedure called Gaussian elimination. So through row operation, we can do the following. Take now, for example, equation number 2. We can multiply equation 1 by a factor that's a21 over a11. And then we subtract the equation 1 from equation 2. If we do so, and then this guy becomes 0. And we can keep doing it such that everything down here becomes 0 by going through all the equations from number 2 to number n. And after we have achieved that, we can go to the next column and treat the smaller m minus 1 times n minus 1 subsystem and do the same thing, multiply equation 2 by a suitable factor and then subtract it from the remaining equations and to make all of these 0. And you can keep doing so until everything below the diagonal, they all become 0. This is called the forward elimination, and the goal is to make an upper triangular system. So to summarize, here is the algorithm. First, we need a for loop to go through all the columns from column 1 to column n minus 1. That means take care of each column in each of the k. And then for each k, we have to go through equation k plus 1, k plus 2 to all the way to equation number n. And therefore we have the second for loop to do that. And then for each j, we'll have to take equation number k, multiply by a suitable constant, a jk over a kk, and then subtract it from equation j to make that 0. And then we replace that for equation j. Okay? And you end your 2 for loops. So note that here, actually, the j and the k are indicating the whole equation. So there are actually many terms in the equation. So there is a hidden for loop in this line here. Let's do a work count. Let's count the total number of flops needed for this forward elimination. So we see basically we have a for loop, kind of a size about n, and embedded with another for loop about size m, but a bit less. And then in here, actually there's another for loop of size n. So roughly speaking, the amount of work will be of order n to the cube, which we wrote here. And if you want to be precise and count carefully, actually it's a bit less, and what you have is a third times n cubed minus n. There is a little bit less work. Okay, but overall, this is a lot of work. Think of n a large number, say n equals to 1,000, and then n cubed is 1,000 million, which is a billion. After the forward elimination, we end up with a triangular system, actually an upper triangular system. So we can start to solve it. Starting from the last equation here, we can solve this and get xn, and plug that back into the previous equation and solve for xn minus 1, and we can keep going up all the way to equation 1 and solve for all the x's. This step is called backward substitution. Now let's put this into an algorithm form. So what you have to do, first initialize, so compute an xn, and then you go through equation n minus 1, n minus 2, all the way to 1. And for each of these I, you keep the xi on the left-hand side and move everything else to the right-hand side because you already know all these xj's, and then you compute it. So we can do a work count. We basically have a for loop here of size n, and inside the for loop, you see we have a summation sign, which means another for loop. So roughly speaking, this is of order n square. If you count more precisely, you actually have a factor of a half n square minus n, because this is like computing the area of a triangle instead of a square, so you get a half. But we will not go into the details of the precise count. So adding up the two steps, and the total work count clearly is dominated by the first step, the elimination step. So it's of order n to the cube. So for large n, this is extremely slow. So therefore, in practice, Gaussian elimination is only applicable if you have a reasonably small system. Okay? For a large system, it really takes forever. Let's take a look at a special system called the tridiagonal system. And that's a system where your A matrix has only non-zero entrance along the three diagonal lines, namely the diagonal, and the lower diagonal, and the upper diagonal. These systems come in many practical applications, and we have seen one when we studied the natural cubic spline, where we end up solving a system of tridiagonal matrix. So here the Gaussian elimination can be very efficient because most of them are zeros, so you actually don't have to compute that much. Okay, so the forward elimination step, so when you take equation 1, when you add it on top of equation 2, you know this guy will be 0, so by your choice of your coefficient, so you don't have to do anything. So all you need to do is modify the value d2 by the suitable factor. You apply it on C1 and then subtract it from it. And for C2, nothing to do because it will be added by a 0. Okay, so the forward elimination actually takes only one single for loop. You just have to go through each equation. And for each for loop, you need to modify the d value accordingly, and also the b, which is the right-hand side vector. It has to do the same operation as the rest. Okay? And after that, you get a upper triangular, upper tridiagonal kind of a matrix A. So it has non-zero around the diagonal and the upper diagonal. So you will start to do a backward substitution. And you see that you can solve for the last equation and plug it into the previous equation and solve for xn minus 1, and then keep doing so. And then for each one, you actually have one unknown that is already know that we move to the right hand side to solve the unknown one. So there's very little work. Let's look at the algorithm. The algorithm says you start from the last one, initialize it, find xn, and then you go back, and then for each I, equation I, you just need to do this simple computation because it only evolves at xi plus 1, which you know at the step. Okay? So this is very little work. Now let's do a work count. We see that basically it's a for loop, and also the elimination is a for loop. So 1 flop, 2 flop, 3 flops, so 3n here, and similarly for the elimination. So total amount of work is some constant times n. So we say it's of order n. So that is very efficient. Well, but as we know, Gaussian elimination doesn't really work for general A matrix that doesn't have this nice structure. So in the end, we'll have to go into numerical approximation, some approximate method that generates approximate solutions.